I just explained you the concept of energy balance between the external work and the internal work, okay? So starting from the work done by the traction, and then we are able to drive the expression of deformation energy density, okay? And then this diagram provides us many informations. For example, actually, the first part here, that represents work conjugate in the structural scale, and which forms the external work. And then the second line represents a work conjugate, the work energy pair, which produce the internal work. Okay, so let's do an example here. Let's imagine a bar here. We have two different cross sections, and subjected to two different forces here. And then let's try to calculate the internal forces. For example, here, then how do you calculate the external forces? If you consider the work conjugate, the external work is equal to, the internal work. The external work should be the internal work, isn't it, right? This is the work balance equation. Then here the external work is what? So work done by the force P1 and the work done by force P2. And let's put a coordinate here. And then I want to put a coordinate in the downward direction. That's why here this is equal to P1 in the UB, isn't it? Plus P2 UC. Okay? This is very simple. This is the external work. Now next step is we need to calculate the internal work. So make sure that the internal work is given in this integration form. So we need to integrate over the volume. Okay, integrate over the volume. So here the calculation of internal work of the whole body is what? We need to calculate the deformation energy for segment 1 and segment 2, segment B, AB and BC. Okay, we'd like to integrate deformation energy density over segment AB and the segment BC. And what do we have to integrate? So we have to integrate deformation energy density. Where is the deformation energy density? Here. Deformation energy density. This is the stress, the work done by stress over the strain. This is the deformation energy density. Make sure the deformation energy density is integration of small deformation energy density. By definition, this is the work done by the stress over the strain. Okay? 0 to current strain. So make sure that stress is equal to elastic modulus times strain. And this is equal to what? A half of elastic modulus strain square. The reason that I put asterisk here is to emphasize this strain is different from this strain. Okay, this is different from this one. This one is just nothing but the integration operator. Okay, if you want, you can use any kinds of variables. Okay, this is a real strain, but this is the integration operator. Any questions? No questions. Okay, so here we need to calculate the stress. We integrate the stress over the strain. Okay, over the strain. And as I told you, the stress is equal to elastic modulus times the strain. So in my lecture note, I put the asterisk in here, the asterisk. But in my lecture note, I just use the same variables to represent strain for simplicity. But anyway, the result is the same. The deformation energy density is a half of elastic modulus times strain square. Okay, strain square, and then we integrate over the volume. That's why area times the length of AB members. And then here's the same, the length of BC members. And then here the strain square is elongation divided by the length, isn't it? So this is square. So let's plug that information into here, then we can obtain this expression. I have one elastic modulus and cross-section area, and then one length, okay, one length, and then another length is cancelled by this length, so I have only the elongation square, okay. And then the BC part, we can get the similar expression here. So make sure that elongation square of AB segment is equal to what? UB minus elongation of AB segment is equal to UB minus UA square. But here UA is equal to 0. This is UB square. The elongation of BC segment is equal to UC minus UB square, isn't it, right? So then external work is linear. As I gave you, external work is linear. So P1 UB plus P2 UC. And the internal work is quadratic. So a half of EA and the length, and then here UB square plus a half EA, the L UC minus UB square. Okay, so external work is equal to the internal work, and the taking derivative also should be also same, okay, should be equal to 0. That's why if you take derivative of this work balance with respect to UB, that should be equal to 0. Okay, UB, that should be equal to 0. And also if you take the derivative to UC, that should be also equal to 0. So we can obtain the force equilibrium automatically if you use the energy balance equation. And for the detailed discussion, please refer to my handout. Probably my TA already posted the handout in the Blackboard. You can refer to all. You can refer to some of some exam problems in this handout. And the next problem is a case with continuously changing load, distributed load here. So even in this problem, the internal work is exactly the same. Okay, so we need to integrate over the volume, and what we have to integrate, and we have to integrate deformation energy density. This is always same. If you consider elastic problem, this is nothing but a half elastic modulus and strain square. Okay. And how about the external work? The external work is we have to, such kind of problem, external work is given by, external work is same. So let's say this is force P, we have to integrate Px, Px, if the force P, this is force per unit distance. And then because we have to change it to the force, we need to multiply Tx, and then this is a vector, and then we have to consider displacement U at that point, Ux. So for the calculation of integration, we need to move displacement into here. This is energy balance for such kind of problem. And then let's consider another example. Here I have a bar here. And then we drop a mass. Okay, we drop a mass, and then because as it touches to point B, and then this point B would be elongated by in a dynamic event, and then it would be elongated to the maximum elongation delta max, and then it turns back in a dynamic event. This is a dynamic problem. But here we focus only, the maximum elongation point. At maximum elongation, because it's going to turn back to original position, the kinetic energy is equal to 0. So which means the energy is balanced. Okay, the potential energy provided by this mass should be equal to the deformation energy stored in this bar. Then how do you calculate the potential energy? Potential energy of this mass, the mass times the gravity. Then make sure that here we ignore the mass of this bar here. So here the drop weight h plus and the delta max, additional potential energy caused by the deformation of this bar. This is the total potential energy of the mass, and that should be equal to deformation energy. Make sure the deformation energy is equal to the integration of deformation energy density over the volume, isn't it right? Over the volume. And then here we have a bar, then this is equal to deformation energy density times the volume of the bar. The volume of the bar is area times the length of the bar. And then here U bar, deformation energy density, is equal to a half of elastic modulus times strain value square. And then strain is given by what? The elongation, isn't it? The maximum elongation divided by the length, and this is equal to a half of elastic modulus length square delta max square. Then if you plug this information into the second equation, a half elastic modulus L square delta max square times area in L. It's cancel. Okay, and then we can calculate out the delta max, the maximum elongation. Using the information of maximum elongation, I can calculate the maximum stress value. It's very easy. Here I have a comment here. Look, in our textbook, sometimes it's pretty confusing, because sometimes they confuse, they describe differently. What I mean, they explain the concept of deformation energy density from two different directions. But look at this. Say I have this is stress strain behavior, and then when we discuss deformation energy density, the control variable is the strain. So make sure the control variable is a strain. This is vector relation. So always, only after we define a strain, so we would like to stress value, okay? Control variable. So which means to represent U bar, we need to, control the deformation energy density in terms of strain, not the stress value. And then here we can consider functional relation from the stress side. Okay, and this is called complementary deformation energy density. So here the complementary deformation density, this control variable, is stress. Okay, they are different, certainly different. In the case of linear elasticity, because the material behavior is a straight line, the numeric value of deformation energy density and the complementary deformation energy density is the same. That's why it doesn't matter whether you use stress or strain as the control variable. But precisely speaking, when we talk about deformation energy density, the control variable should be the strain. Okay, please keep in mind this. This is very important. Okay, so if you don't have any further questions, I want to consider some more advanced topics here. So the first one is the premature failure by fatigue. And then here, let's look at this. Let's say okay, so when we design my structure, for example, let's consider I have a one-dimensional problem that is subjected to force P, and this force P produces some normal stress. So in our discussion, if normal stress is far less than the yield strength value, so we can say that my structure is safe against the loading, isn't it, right? For example, my stress strain behavior would look like this. if you consider just structural steel. And my current stress value is less than the yield strength value. Current stress is less than the yield strength value. So in our static analysis, we'd like to say that this is a safe condition. Okay. But now at this point, everybody knows that if you apply the loading, repeatedly, okay, then it's gonna lead the structure failures, okay, and that behavior is called fatigue. This is the fatigue loading. The fatigue is another word. Fatigue is premature failure. Even if the stress is the stress range is less than the yield strength value or any strength value considered in the design of structure. But if the stress is applied repeatedly to the structure, then the stress history would lead the structure fail. Okay, and then there exists so-called endurance curve, so-called SN diagram. Okay, SN diagram. The vertical axis is stress, and then the horizontal axis is number of cycles, and that this curve represent, for example, let's say you consider 100 megapascal. The range of stress 100 megapascal. So if you apply the loading repeatedly, and then if it failed in 10,000, okay, 10,000, and then also if you do the same thing with the lower stress value using the 80 megapascal, and obviously because stress range is smaller than that, then our life of the fatigue life would be greater than before. For example, 20,000 cycles. Okay, so we have to do the test for all these conditions. Then we can obtain a diagram, so-called SN diagram. Okay, SN diagram. And then typically the safety against fatigue is evaluated by the SN diagram. Okay, SN diagram. So because this issue is beyond the undergraduate students, so we don't want to consider the fatigue behavior, but keep in mind that there is an issue of fatigue, okay, fatigue. And then when you design steel structures, the fatigue is very important, and especially your structure is subjected to repeated loading case. So we always need to check the fatigue. And then, for example, when you design offshore structures, the fatigue is very important. And then the second issue is Saint-Venant principle. So far, when you consider one-dimensional problems, we considered only the average, average stress value, not the average. We assume the stress distribution of stress is uniform. So when you calculate normal stress, we just divided the magnitude of force by the area of the cross section. But in reality, it is not the case. So if you apply loading to the load point, then the stress below the load point is much higher than the nominal stress value calculated by using this equation, P divided by cross-section area. This is pretty obvious, isn't it? And then, but in this principle, this stress concentration by the load point, the concentrated load, is quickly decays away to produce almost uniform distribution of the normal stress. Typically, in distance equivalent to the width or the diameter of the same bar, so we can assume that the stress distribution is almost uniform, as we consider the one-dimensional example. Okay? So in reality, there is stress concentration. And then the third one is stress concentration factor. In 우리말 응력 집중 계수. Okay, in our discussion, even if we have a hole, so we assume that we just consider net area, for example, to calculate the stress value. we divide the load by the net area, A net, isn't it right? So A net, that's what we did. Okay, so we assume the uniform distribution of normal stress when you calculate normal stress, but in reality it is not. The stress is concentrated to a point where we have irregularity in dimension. For example, near the hole we have higher stress value. This higher stress value divided by the nominal stress is called stress concentration factor, 응력 집중계수, stress concentration factor. And there is a handbook for the stress concentration factor depending on the geometry. Make sure that the stress concentration factor surely depends on the geometry, okay? So if you open such kind of textbook, in this textbook, for example, look at this size of the hole and the width of this member, okay, width of this member. Then if the D over B is very small, then we have high stress concentration factor, almost 3, and then it depends on the geometries. And even for this, so whenever we have the change of geometry, we have stress concentration, okay? So this is very important to note. So whenever we have change of rapid change of geometry, so we need to consider stress concentration factor, and there is a handbook for the stress concentration factor. For design purpose, you need to calculate the normal stress by using just one-dimensional consideration, and then you need to multiply the stress concentration factor to your calculation. And how about the nonlinear behavior? Nonlinear behavior, although we are talking about the linear elasticity, but the nature is there exists plasticity. For example, if you consider reinforcing steel, the behavior of reinforcing steel can be modeled by elasticity and plasticity, isn't it? So this kind of smooth curve can be approximated by bilinear curve. Initially linear elastic branch and then strain hardening branch. And also in the extreme case, we can consider linear and the perfectly plasticity behavior. So although we don't want to discuss the plastic behavior in the mechanics of material class, but in the class of reinforced concrete design, reinforced concrete structures, and then also the soil or the foundation, the engineering of foundation, the consideration of this plasticity is very important. Okay, here I'd like to finish my lecture. Do you have any questions? So I hope here, the discussion regarding the deformation energy would be very useful for you guys. You can obtain the general, overview regarding the energy issues. So there are various different forms of energy approaches, but the starting point is always same. So we need to consider the energy balance between the two different forms of energy. Do you have any questions? By the way, today we have a TA class, okay? Okay, so if you don't have any further questions, let me start my lecture here. And then if you have any questions, please, you are very welcome sending emails to my email address. So let me start my lecture here. See you next time.